Hi, my name is Reed Andrews, and today I'll be talking about methods that we've developed for automatically tuning arrays of quantum dots, and particularly those made with the SLEDGE process. I'd like to take a big picture, so we'll start at the top and then dive down layer by layer, uncovering a few issues and then build back up. And so there are many ways to build a quantum computer. One of them is using an exchange-coupled fabric, and so I'll describe that, why we make that choice. And then when it comes to making an exchange-coupled fabric, reality bites in a few ways. One of those means that we have to deal with disorder that's present. I want to touch on that. And then how we deal with disorder is that effectively means that we have to make a series of measurements. And so to do this automatically, we need to establish a process loop. And what that boils down to, making that loop work, means that if we have a way to collect data and really get the information we want from that data, which is the final thing at the bottom here, then we can make this work. That allows us to tune up devices, set voltages, which we need, and then go on to characterize qubits and demonstrate 2-qubit operations. So let's start at the top. We choose to implement quantum computation with an exchange-coupled fabric, and we do this by trapping electrons. And we confine electrons in the vertical dimension using a silicon-silicon germanium heterostructure, and then we confine them in the lateral direction using patterned metallic gates. And then we perform manipulations on the spin state of these electrons with pairwise interactions. And the pairwise interaction is effectively you couple individual spins, and so the interaction is diagrammed on the right here. However, due to the symmetry of the exchange interaction, and just that it requires 2 particles, it means that to make a qubit, we need 3 electrons, and we need to couple those together. And effectively, it means that our Hamiltonians, our interactions, are in the single spin basis, but then we encode our qubit in a 3-electron coupled spin state. But if we do that, it allows us to control the state of the qubit solely with baseband voltage pulses, which is diagrammed a little bit on the left here. And importantly, this exchange interaction, it's extremely highly tunable. We can easily get more than 5 orders of magnitude in dynamic range, and this is because the exchange interaction is caused by overlapping the wave functions of the electron. And I like to think of it as we can either make electron soup by pushing these electrons spatially together, or we can effectively separate them. And this allows us to turn the interaction on or off with a lot of dynamic range. The one downside to this approach is that 2-qubit operations typically require on the order of tens of pulses. And that's due to the symmetry in the exchange interaction and the encoding and how the dots are connected, how the electrons are connected. But the bottom line is that exchange provides a really highly tunable interaction that we can use to manipulate qubits. Okay, so we've made a choice that in order to do quantum computation, we want to do one thing, exchange, and do it really well. So how do we implement or make an exchange-coupled array? We do that with a process that we call SLEDGE, which stands for single-layer etch-defined gate electrodes. And one of the primary innovations here is a separation between the front end of line and the back end of line. And the front end of line here consists of the gate dielectric, which lies on top of that silicon-silicon germanium sandwich, and then the gate metal, which is titanium nitride. And the back end of line consists of patterned interconnects, which then go up and fan out to bond pads. And to give you a better idea of what this architecture looks like, this is an SEM image of the gate metal on the surface. And so then there are dots that are patterned and combined with bath gates and then field gates. And now importantly, vias are routed upward and then they fan out to bond pads. And then if we zoom in and take a slice, this is that TEM that I was showing before. So a qubit is composed of 3 trapped electrons. And then we interact these electrons with pairwise in order to manipulate the qubit. And the pulses here, they're tracing out a specific sequence, which is a Fong10 C0, or effectively a 2-qubit entangling gate. So one of the main takeaways from those videos is that these SLEDGE arrays, they're really controlled by voltages. And so for the 6-dot devices that we have here, there's 26 voltages for 2 qubits. And that turns into, well, that's 13 voltages per qubit, or if you want to round down, it's about 10 voltages that we need to set in order to operate a single qubit. So apart from just this problem of setting a voltage, what we're really trying to do is control the electrochemical potential in the quantum well. And so in the lower left here, we're really trying to set it so we have one electron trapped under each dot and control the wave function overlap to control that exchange, which will control the qubit manipulations. You can ask, why can't we just set the voltages? I showed you images that have materials and dimensions, so why can't we simply solve the electrostatics problem and deterministically set our voltages? And we can't do that because there's disorder. There are several types. Maybe the simplest one is that there's like fabrication tolerances, which means that the size of the gates, we only know them to within about 10 or 15% when they come out of fab, and so the voltages have to be adjusted accordingly. But perhaps more importantly, there's disorder and trapped charge at the surface. And we can ask, what effect does this have on the electrochemical potential in the quantum well? And we can get a feel for this by scattering in simulation charge across the surface and then asking what the potential in the well looks like. And so these diagrams here in the middle are doing that. One is for a 10 nanometer SIGI cap and one is for an 80 nanometer SIGI cap. And this is the distance that the quantum well is from the top, from the front end of line. And the circles and squares, those are the dot gates and the barrier gates shown for scale. And what we can see is for the 10 nanometer cap, there's potential fluctuations on the order of 50 MeV, but perhaps more importantly, the length scale is quite short. Whereas if we go to the thicker SIGI cap, the magnitude of the fluctuations are reduced to around 15 MeV, but perhaps more importantly, that length scale is longer. So if our task, which it is to really control that electrochemical potential, we have a much better chance of doing that with the thick SIGI cap because the potential, that disorder potential, is slowly varying. In those images above, used a charge density of 40 to the 11 per centimeter squared. You can ask, does that make sense or where does that come from? And the short answer is that's very consistent with measurements. We have a measurement technique where we can directly probe the disorder in the well, which we do by loading a dot with one electron and then coupling it to the bath with a known tunnel rate. And then we can record the voltage difference between the voltage on the dot and the voltage on the barrier. And if we do this for several samples over a variety of different silicon germanium cap thicknesses, it's really the scatter in the points, the scatter in these black points here, that's consistent with the around 40 to the 11 per centimeter squared charge scattered across the surface. But the bottom line here is that we expect to have to individually adjust gate voltages to compensate for disorder. And also the presence of that silicon germanium cap, that's really nice. It makes the problem tractable. Okay, and so now back to the outline. It shows to do exchange when we implement it. We have to go vertical with this back end of line. One of the side effects of reality here is that we have to deal with disorder, and that means that we have to individually tune each of the voltages, of which there are about 10 per qubit. In order to deal with this disorder, we're going to have to make a series of measurements, essentially figure out which voltage we need to set the gate to. And so to do this in an automatic way, we really want to set up some process loop, where we're going to start with data collection, then we're going to move on to analyzing that data somehow, take the results of that analysis, store it in a model, and then use that model to determine what to do next. And then when we know what to do next, then we can set up our instruments, take data, and allow the process loop to continue. And this is really what a human does mentally. We take data, we figure out what information we want, we stash it away, and then we intelligently figure out what to do next. And we're just trying to write that down formally. But one key thing here that I want to point out is that success at each stage of this loop just means that we can continue the loop. We know what to do next. And that's really the threshold that we're going for. And one additional thing that I'd like to point out as we talk about automation and automating setting these voltages, I really want to focus on how long it takes to tune a unit cell, however we choose to define a unit cell. And that might change in the future as we have more layers, more metal layers in the back end. We really care about tuning a unit cell and then scaling that in the future. And in particular, if we have an automated method, that can scale quite well with additional measurement channels. A human, we don't parallelize so well. When it comes to what measurements we'd like to make and what analysis we'd like to do, I think it's worth starting with what are we measuring? And our groups, our group at HRL, just like many other dot groups, we effectively measure the electric field, and in particular changes in the local electric field. And we do that by flowing current through the quantum well, as diagrammed here. and we force it through a particular channel that's controlled by this gate, the M gate, and we set the voltage on the M gate so that any change in that M gate voltage, which means that by extension means any change in the local electric field, causes a high change in current, essentially these Coulomb peaks. But one thing that I do want to point out is these Coulomb peaks, they're narrow, so they have a high differential, so a very sensitive probe of electric field, but also they're narrow, which means that they have limited dynamic range. Once we've established an electric field sensor, we can use that to probe the state of the other dots in the array. And we typically do this by just sweeping voltages, sweeping the voltage of a barrier gate and a dot gate, which is shown here in this figure on the left. And we usually also apply a modulation to that dot gate. And the result of sweeping those voltages and monitoring the local electric field, that's shown in the lower left or lower right here. And so there's lines, and those lines correspond to changes in the electric field, which are where we've loaded an individual electron underneath that dot. And these lines don't extend forever. In particular, there's what would be called the slow point, and that's limited by the chop time or the modulation time of the signal that we apply to that dot gate. And in this case, that corresponds to a time of about 10 microseconds. And then it's also limited on the other end by the amplitude of that modulation, which in this case corresponds to about a picosecond. And the main takeaway for this slide is that when we take a scan or when we sweep voltages and monitor the local electric field, the features that we see in that scan, they correspond to physically meaningful values. And to interpret them, we also need to know how we set up our measurement and the measurement parameters. And so when it comes to making a process loop, we can take the scan and we can ask what information is really key? What information do we want to extract? And so what I'll propose here is that what we'd like to do is we'd like to extract a set of vertices and then a set of edges that relate those vertices, where we have two types of vertices, one for these fast points, and then another type of vertex for the slow points, and then edges that relate them and tell us how to change charge occupation or alter the barrier, alter this coupling rate or tunnel rate. And just to be pretty explicit, you can ask, well, what does this point, this 1 point in voltage space mean that's halfway between the two lowest fast vertices, if you will? And so first, it means that that dot has a single electron in it, and that dot will reach its equilibrium electron occupation in about a picosecond. But perhaps more importantly, it means that if we maintained the electrochemical potential beneath those gates, while we added an additional electron, as shown in the middle here, the lower middle, that would mean that those two electrons are now coupled with a tunnel coupling of about 100 gigahertz, just using Fermi's golden rule and an estimate for the density of states. And then additionally, if we can estimate or have independently measured the excited state energy, then we know the exchange energy, which in this case is about 100 megahertz. And this exchange energy is really how fast qubit is going to rotate. It's that that tells us about qubit manipulations and manipulations of electron spin. And so the point here is that even from simple scans, interpreted correctly, we already are learning a lot about the quantum operation that we'd expect from these arrays. And so in addition to the dot loading scans that I was showing, there's the very common dot coupling scan where we'd sweep the voltages of two plunger gates and we get a double dot charge stability diagram, which has this, in some ways, famous hexagonal structure. And we'd like to extract that hexagonal structure from any scans, because that's going to allow us to traverse these charge stability diagrams and, for example, easily go to regions where we can do spin-to-charge conversion or read out the spin states of our qubits. And so what we're doing here is we're committing to a certain type of analysis. We're saying that we would like to input a scan and get out a graph. And just to be very explicit, what we mean by graph is a graph has a set of vertices and a set of edges. And the vertices are a matrix, or they just have some number of vertices in that matrix. And then each vertex has a number of attributes. And then similarly for the edges, there's an edge that relates each pair of vertices, and each edge will have attributes as well. And then when we go to display these graphs, we place vertices and we color them. So we place and color them according to their attributes. And then similarly for the edges. But long story short, the input is a scan and the output is a graph. That's the analysis that we're committing to. And as a reminder, we'd like to do that, or we think that's a reasonably good choice, because it allows this process loop to proceed, where we can collect data, analyze that data, crunch it into a graph where we really want to maintain all the information, or as much information as we can, and then use that to update our model. So that then when we move to determining the next step, we can decide what to do next using simple physics-based rules, which is what we'd like. And underlying this is that we're really trying to separate the data analysis from the decision making. And we're not framing this as an optimization problem. We can reduce it to an optimization problem, but for the time being, we'd like to keep the flexibility. Okay, so back to our outline. We've chosen to do one thing, exchange, and do it well. When we implement that, when it becomes reality, we have to set each voltage, and then to figure out how to set each voltage, we need a process loop. To keep this process loop going, we've decided that we need an analysis that's extremely robust and allows us to convert a scan into a graph. It's worthwhile just to point out the scope of the problem. Those scans that I was showing you earlier, I would classify those as quote-unquote pretty. However, the data that we see, I've diagrammed some on the right, some for dot loading and dot coupling, it has a larger variety of features. And there's several sources of variation in these scans. One, as I pointed out earlier, can be saturation or drift in our electric field sensor. And that's actually very visible in several of the scans and the high contrast where it goes from white to dark. This also causes features to wash out or sometimes low signal to noise. We also have an issue where if we don't know the coupling rates or the tunnel rates at all, our array won't reach equilibrium during the time which we're taking the measurement. And this kind of washes out some features, maybe shown a little bit in some of the scans on the lower right. And then there's also some natural disorder and variation that's present in a lot of the scans as well. And so I guess I do want to be clear. So these data are all from quite working devices, but it's just when we initially turn them on and we have very little idea of how they function or where we are, that the data can be a little bit noisy and hard to deal with. Once we know what we're doing, or once we know in voltage space and we've already characterized the disorder, the scans become quite much nicer. So we've established two training sets, or two data sets. For dot loading, it's about 800 scans, and for dot coupling, about 500. And what we're trying to do is extract graphs from all of these scans. And I do want to point out that our scan variety is probably comparable to other work out there in the field, as shown in the lower left here. Okay, so our task is to take a scan and convert it to a graph. And we're going to choose to do this with an artificial neural network. So as we attempt to accomplish this task, we don't have a ton going for us. We don't have a lot of data. And there's not a lot of analogous problems. Our data is a bit unique. We do have one thing going for us, and that's that the graphs that we're looking for, they have a structure in voltage space. For the dot loading, they have that ladder, or for the dot coupling, they have that hexagonal pattern. And so we'd really like to leverage that wherever possible. And so when it comes to artificial neural networks and image analysis, or that type of analysis, convolutional neural networks come to mind. A convnet takes in a scan, or an image, and then it typically outputs an image with reduced pixel resolution, or in our case, reduced voltage resolution, but it has more channel information, more features. And so convnets are very fast and parallelizable. Their translation invariants are actually equivariants. It's not great at capturing this long-range structure that we want, though. So there's advantages there, but we need to be a little bit careful. And then in a normal convnet pipeline, the output of that convnet, it goes into a global average pool, which averages over all the pixels. And so there we'd lose all structural information, so this global average pool is something we probably want to stay away from. And then finally, there's an MLP. And this MLP typically operates over channels, which makes a lot of sense. If we do want to apply it over pixels or voltage space, we can. We just need to be a little more careful. But overall, convnets, they're great at identifying features, and that's a strength. But when it comes to piecing them together, they struggle a little bit, and so we need to be careful. So when it comes to the application that we're looking for, we need to look a little bit farther. And so on this slide, I've moved the convnet up to the top, and then looking for other methods. There's dictionary lookup for language processing, which is very commonly called attention, and this starts to feel very much like something we would like to use. And so this dictionary lookup, it consists of a sequence of queries, and then we pick a query, and then we compare it to a sequence of keys and compute a similarity measure. And then based on the results of those similarity measures, we create a weighted sum of the values and use that as the output sequence. And so this dictionary lookup process, it's long range in the sense that a query is compared to every other key. And it can also really recognize structure, particularly if that is encoded in the keys or the values themselves. However, we do need to be careful because that similarity measure really relies on the information in the queries and keys being in some sort of meaningful space. So when you compute a similarity measure, you get a meaningful output. And then additionally, this type of operation, the output is a sequence, and this starts to look a lot like the sequence of vertices that we'd like. Yeah. And so before I was saying that covenants, they're good at identifying features, but less good at piecing them together. Almost the opposite is true for this dictionary lookup, where this attention, it's good at piecing together features, but it's less good at identifying them. And so perhaps unsurprisingly, we're going to create an artificial neural network tailored to our application by just mashing the two together, where we're going to take a scan, pass it through a convolutional neural network. The output of that is going to be reduced voltage space, but each point or each pixel is now going to have a lot of channel information. And then we're going to stamp each of those vectors with the coordinates, and then just unroll it into a sequence, and then pass that sequence into our dictionary lookup. The result of that is going to be a sequence, which we then process channel-wise to get a set of vertices. And then we perform a self-similarity and then a slightly different MLP to get our edges. But the bottom line here is that we're creating a neural network tailored to our application by combining elements from computer vision and natural language processing. And so now we have a network that can recognize this long-range structure, but I haven't told you how we really use the notion of this pattern, that we have a hexagonal or ladder pattern. And we really do that when we go to train the network and we encode it in the loss. And so to describe this, our network, it outputs a prediction, which I've diagrammed here, predicted graph. And part of the loss, we'd like to ask how much energy does it take to deform that prediction so that it matches the label when we treat those edges as springs. And here we're effectively comparing the length of a predicted edge to the length of a ground truth edge or an edge in the label. And this gives us a long-range interaction that really forces or encourages our analysis routines to respect and learn about that long-range structure. And so we can evaluate the performance of these networks on simulated data sets. Simulated data is great because we can create thousands and thousands of examples. In this case, we go up to 20,000. When we train our network on this and then evaluate or create an F1 score on the validation set, we get about 0.9, which is very close to perfect for this data set, given the information that's available in there. However, as we train our networks with fewer and fewer examples down to a few hundred, it still maintains very high performance. And this is extremely important to us because our data sets aren't that big. Okay. And so we can take these analysis routines, train them on the data sets that I showed before, and the results are shown here. So on the upper left, these are the scans that I was showing before, and then on the right, those are those same scans, but with the extracted graphs overlaid. And overall, it does reasonably well. There are some localization errors in the scans on the top, and then in the scans on the bottom here, these dot coupling scans, most of them are pretty good. There's one in the middle here that doesn't make a ton of sense. But overall, if you ask, does the result, does it allow this process loop to continue? The answer for all these is yes. Okay, so now I've described how we can robustly extract graphs from the scans that we collect during our process loops. And so now we can start to automatically set voltages. And so here's our process loop shown at the top. And now what we need to do is nest, stack, sort of hierarchically organize, however you want to phrase it, a variety of these loops to successfully tune up the dots. And the steps that we take, they align pretty well with the steps outlined by Justina Zwolak and Jake Taylor in a recent colloquia that they posted to the archive. And in the next few slides, I want to focus on 3 steps in particular, this dot loading, gate virtualization, and dot coupling. And what our algorithm that we use for these steps is pretty similar in spirit to that used by Volk, their N+1 algorithm that they described in 2019. Ours is a little bit different. We've modified it, but importantly, we've automated it. We've removed any human element. And so on this slide, I try to describe to the extent we can an algorithm. And so at the very top here, this is a timeline where we start at 30 seconds or near 0, and we end at around an hour. And then during that time, we run 2 primary routines, which we call auto PVT and auto PVP. But auto PVT, it starts with the no electrons in the array, as diagrammed here. And then as auto PVT proceeds, it scans out or sweeps out voltage space, collects data, and then we analyze it, extract a graph, and then based on that graph, we set voltages. In this case, we're choosing to set the voltages so that there's 1 electron in the dot, and there's about a femtosecond tunnel time. And so when auto PVT ends, we end with most of these barriers fairly transparent with 1 femtosecond. One's opaque, and then one's a little bit coupled. And that's because we're going to go start to pairwise couple these electrons. And so auto PVP, that function does the gate virtualization and coupling, and then it ends with an electron under each dot coupled at around 500 megahertz to a gigahertz. That's something adjustable, but in this case, that's what we're targeting. And I want to show a few of the scans near the end of this algorithm. So for this P2, P3, where it's coupling 2 dots, the scan shown is here. Here we're running into a little bit of metastability problem, where because we're targeting a relatively low coupling rate, the array's not reaching equilibrium, and so some features are pretty weak. However, our analysis routines can really hang on, and they allow us to still correctly identify the 1 electron, where we have 1 electron in each dot. And the P1, T1, this is just an example of collecting that scan and setting it to a little bit lower, in this case about 10 nanosecond dot relaxation time. And this final scan is, again, just another it's a dot coupling scan, or double dot charge stability diagram, where we can successfully identify the 1 electron state. And so we can apply these routines across a variety of devices. And here we've tabulated statistics for 5 devices. The bottom line is that it can tune up these arrays, these 6-dot arrays, in a little bit under an hour. Compared to a human, it's around 90 minutes to 2 hours. And then 2 things I want to point out. One is that it's really those initial sweeps, this auto PVT, where we just don't have much information and we're sweeping out voltage space. Those take the most time, 43%. And then also, additionally, the virtualization step, it takes a big chunk as well. So we have our eye on those, or how to do those more efficiently. But our routines quickly and robustly tune SLEDGE devices. However, one of the things that we're pretty excited about is that we have a very strong foundation for moving to spin readout. And that's because with these graphs, we can very easily go to what we call the 1,1 or 0,2 electron occupation, which is necessary for spin to charge conversion. And so that covers all the topics I wanted to, where we started with choosing to do quantum computation with an exchange-coupled fabric. And then implementing that means we have to deal with disorder. In order to deal with disorder, we have to make a series of measurements. And in order to keep the automation of those measurements going, we need to extract the information that we need from the collected data, and we do that with a graph. And then once we've done that, we can tune up these arrays in a little bit less than an hour. And that provides a strong foundation for moving on to characterizing single qubits and demonstrating 2-qubit operations. And I can't help but mention the punchlines for these 2 talks. One, that we have well-understood error sources, and that we can do a half-decent 2-qubit gate. But again, if you're interested in these topics in more detail, I'd highly recommend the talks by my colleagues. And so with that, thank you very much for your time and attention. And we are hiring, so if you like the topics that we covered today, and particularly starting at the top and diving down to a few technical details and building back up, yeah, we'd like to hear from you.